Alright, so now I want to talk about homogeneous equations, and mainly to just try to help you avoid being confused about this word homogeneous. We saw earlier in the course that there were first order homogeneous equations, and they had a specific format. And that's what this first notion, numbering 1 for the first idea, is a first order equation was homogeneous if it had this form where this expression involving our unknown function y and the independent variable x happened to satisfy this algebraic condition that if you multiply x and y by the same constant t, then algebraically it'll somehow simplify and the t's will go away. This special structure allowed us to solve those problems by basically doing a substitution which reduced the problem to a simpler kind of problem, a separable equation. So that is homogeneous, and the homogeneous has to do with somehow independence of constant multiples. That's the words you should think of. This function f is independent on multiplying its inputs by the same constant. If you do that, it doesn't change the value of the function. So that's what homogeneous means in that sense. For the rest of the course, we're talking about linear equations. A linear equation is going to be called homogeneous if the right-hand side of the equation is 0. And why we call this homogeneous is for the same idea, but it's not the same concept. It's because if we have a solution to this equation, then any multiple of that solution will also be a solution. So for example, if I find a function y which solves my homogeneous equation, L of y equals 0, then if I plug in, say, 10y, let's just imagine c is the number 10, into my linear differential operator, because it's linear, the 10, or the c, factors out. And I'm left with L of y times c. But L of y, we already know, is 0 because y is a solution. So therefore, we also get another solution by 10y, or c times y. So any constant times y is also a solution. That's what homogeneous means in this second sense of the word. But these two senses are they're not the same concept in terms of differential equations. The first one was for first order equations, which were not necessarily linear. But the second one, we're totally focusing on linear equations. So L of y has to be a linear differential operator. And the right side would have to actually be 0, and that's what we call homogeneous. It's this property that allows us to solve the homogeneous part of the problem. And when we find those solutions, we can multiply them by any constants we want, and we still get a solution. So this is what allows us to introduce those constants, C1, C2, and so on, so that we can construct our general solution. So looking at some examples. We have this equation here. It's a second order. It's linear because y prime and y double prime, if they appear, they all appear in one term by themselves, and they're only multiplied by some other stuff, like other functions. But in this case, they're constants. So this equation is a second order linear homogeneous equation because the right-hand side is 0. And it has constant coefficients because what we're multiplying y prime and y by is just numbers. So we don't have x or e to the x there, we just have numbers. So second order linear homogeneous equation with constant coefficients. Next example, it's a third order equation. So the third derivative is the highest derivative we see. But again, notice there is no y in the equation, but that's okay. The third derivative, the second derivative, and the first derivative are there. They all appear in one term by themselves, and they're each raised to the first power. So this is a linear equation. It's homogeneous because the right-hand side is 0, but it does not have constant coefficients because the second derivative term has an x coefficient, a functional coefficient. that changes depending on what x is. So this is a third order linear homogeneous equation, but we can't say anymore. It doesn't have constant coefficients. Let's look at three examples which basically show us that these two concepts are actually different. If we look at this first equation here, we can rewrite it, if we wanted to, as y prime equals negative 5y over x. That satisfies the first definition of homogeneity. In other words, if we let f of xy be negative 5y over x, then this will be true. So it is a first order homogeneous equation, like we talked about before. But it's also a linear homogeneous equation because, look, we have two terms. There's a y prime term and there's a y term. The y is multiplied by the function 5 over x, so it has a functional coefficient, so this is linear. And the right-hand side is 0. So this example satisfies both types of homogeneous equations. The next example, all I did is I changed the right-hand side to a number that's non-zero, 3. So this is no longer a linear homogeneous equation because the right-hand side is not 0. But if I solve this equation for y prime, I have y prime equals f of xy, where f of xy is just 3 minus 5y over x. This still satisfies the first definition that we talked about for homogeneous. So this equation is a first-order homogeneous equation, and it is a linear equation, but it's not homogeneous in the sense that the right-hand side of the equation is 0, because it's not. So it satisfies the first type of homogeneous equation, but it doesn't satisfy the second type that we talked about in the previous slide. So it satisfies this first one, but it doesn't satisfy this second one. Then our last example satisfies the second type because the right-hand side is 0, and this is a linear equation. But it fails the first type, because if I solve for y prime, I get y prime is negative xy. So my f of xy is negative xy, which is not equal to negative tx times ty, which is what f of tx comma ty would be. So it fails the first type, but satisfies the second type. So these two notions of homogeneous are very different. They do overlap. There are some problems which satisfy both, but there are problems that satisfy one and not the other.